Zhu from UNLV, who is visiting us, and he will speak in a little while about something else. Just wanted to alert everyone that tomorrow at 7:45 a.m. The Cassini mission will smash into Saturn. And so that's something to watch out for. We will lose contact with it, and this device will basically evaporate as it plunges into the planet. So that's an interesting event. We'll start today with Adam Rubin from the Wiezmann Institute, who will tell us about the observations of young supernovae, the new instruments to study them. And then we'll hear from Zhaohuan about the observables of circumplanetary disks. And then from Jennifer Johnson from Ohio. Where is Jennifer? Okay, whatever. She will tell us about elemental abundances in Dwarf planet hosts and implications for rocky planet dynamics. And finally, from Piero Rosati, who is visiting us from the University of Ferrara. Piero here, yeah, over there. He will tell us about the Dwarf's high-precision, strong lensing modeling. Yeah. Adam.
So, thank you very much for this opportunity. Now, today I'm going to tell you about our observations of Type 2 hydrogen-rich supernovae in the first few days after explosion. And then I'm going to tell you about a new design for a UV visual instrument to study them. So, the reason we're so interested in the first few days after explosion is that the emission encodes a lot of the important physics of the progenitor system and the explosion itself. The reason we can relate them back is that in early times, there are some simplifying conditions. The ejecta is extremely hot, therefore the plasma is fully ionized, and the emission is coming from the outer edge of the ejecta, which means that the hydrodynamics are relatively well understood. This means that we can relate back using shock cooling models what the progenitor system or certain properties of it were. Another interesting part of the first few days of emission is that the circumstellar material, so this is material that was ejected from the massive star prior to its death, is still in the vicinity. It's far enough away that it can be ionized early on, emit some of that radiation to us, and then we can see the fingerprints of some of the material that was on the outer edge of the star before it's completely obliterated by the expanding ejecta. And finally, it's really frontier territory. So we haven't been able until recent years to observe these supernovae in the first few days very systematically. So there's some low-hanging fruit here, and we'll discover new things no matter what. So in the last 3 or 4 years, large samples have come out, and people have done analyses to study the whole zoo of type 2 hydrogen-rich supernova light curves. There are some that are plateau-like and flat, some are linear declining, and it's not really well understood what's driving that diversity. And one thing that was discovered was there's a triple correlation. So the peak magnitude of these type 2 supernova light curves is correlated with the decline rate. So brighter supernovae decline faster. And that's thirdly correlated with the H alpha equivalent with absorption to emission ratio. So brighter decline faster, have shallower and weaker H alpha absorption. And currently, this is not really well understood why this is the case and what are the driving parameters. Some speculate this is the mass of the envelope, but it hasn't been shown yet. So we established this, the peak magnitude and decline rate correlation on an independent sample in R-band from the Palomar Transient Factory. Now, our sample is really special in that, as I said, we have actually the full rise information. So we can really well constrain the rise time of these supernovae. And one of the most first questions we wanted to ask was, how does that factor in to this correlation? Is it correlated with the other parameters? And surprisingly, it's not. So what you see here is the rise time in rest frame versus the peak magnitude. And as you can see, it's completely uncorrelated. And it's kind of exciting in a way because it means that it's well worth our while to invest more resources in studying this early time, because we're actually probing a part of the phenomena that could be independent from the rest. So if at the beginning we're talking about the cooling emission from the ejecta, at later times recombination and nickel radioactive heating may take effect. So this is a really special window which we can observe. We then took this and actually compared it to shock cooling models. So these models describe the emission from the cooling ejecta. And in the first few days, it can be related back to the radius and the energy per unit mass in the explosion. Now, what we found was that with 33 light curves from PTF, in R band at R cadence, it wasn't really possible to constrain the radius in a meaningful way. However, the energy per unit mass was constrained and is correlated with the amount of nickel produced. Now, this result is new and can be used as a benchmark against which to test alternative models for the explosion mechanism itself. So what we see here is that stronger, more energetic explosions produce more nickel-56 in type 2 supernovae. Now, if we can't constrain the radius from a single band, perhaps we can do it with multiband. And we did this. This is a difficult measurement because it's hard to get all of the resources. But this was a very special supernova, SN 2013 FS, where we were able to get on target and get photometry and spectra within a few hours from explosion, all the way through a few days. You can see here on the left observations from the ultraviolet all the way to the infrared. And we were able to use this information to constrain the radius and energy per unit mass of this supernova to be between roughly 100 and 350 solar radii. Now, this is somewhat surprising because most of our current expectations, also from pre-explosion imaging, is that type 2 supernovae arise from red supergiants, which are more in the range of 500 to 1,000 solar radii. So this is a little small. However, we can, using simulation, I actually looked at these models and we explored what kind of observations would give us the best results. What do we really need to constrain the radius tighter and tighter of these events? And the answer is ultraviolet coverage. Now, the main reason is that, as you can see here, the temperature needs to be hot for us to be able to use these models. The plasma needs to be fully ionized, or else the assumptions of the models break down. Now, the rise time is what gives us the best handle on the radius of the progenitor star. So we need a photometric band which rises to peak from thermal cooling fast enough so that when it reaches the peak, the temperature is still above 1 eV. And that's true for ultraviolet. So by about 2 days in this simulation, the ejecta is still hot enough that the models are valid. So you can see here in the inset, the gray is what you would get from an optical band, from G band, for example, where the radius is completely unconstrained, and the blue is for UV, where you can see the radius is much tighter constrained. And if you have both, you can actually begin to constrain the local host extinction, which is a parameter which has only been measured via proxy until now in supernovae. Now, I said at the beginning that the CSM, the circumstellar material, is also around to give us fingerprints of what was the composition of the progenitor star. And in 2013 FS, that supernova that I showed the light curve of, we actually got a full spectroscopic sequence from hours to days. And one of the striking features is these narrow lines, and one of the key ones is helium-2, which you can see at the top and slowly disappears by a couple of days. And our interpretation of that is that this circumstellar material emitted this radiation. It was ionized by the shock breakout. And then as the ejecta sweeps it up, it disappears. Now, how are we going to get from a chance event like this, where we were lucky and able to get on target and mobilize all these resources, to move into a systematic study of these? How are we going to get, we need more spectroscopic resources to be on target faster and get full coverage. So we joined the SOX collaboration. SOX is an acronym for Son of X Shooter, and it takes, it's a replica, in some sense, of the X Shooter original design. One of the key features, which is that it's broadband, so you can go from 0.35 to 1.75 microns in one exposure, one go. And I say it's in some way a replica because our main contribution to this was offering a different design. So what you see here is the multi-imaging transient spectrograph, or MITS, so SOX and MITS. And the way it works is separating the spectrum into subbands. Now, that's done by an elaborate feed mechanism, which I don't have time to really show here. But what I want you to understand and what we're looking at is you can see the four bands roughly correspond to, let's say, U, G, R, and I. And those squares that they hit are optimized gratings. So they can be, there are a few different technologies. They're at order 1. Okay, I'll be very quick. They're at order 1, and we use a single detector to get all of them onto the, we have a single detector for all of them. And the Sagib and Ami here at the SAO helped us a little bit with the concept. Just last slide, in terms of performance, our PSFs are well contained within 2 by 2 pixels, less than 0.3 arc seconds diameter. The resolution is what we need for this instrument, between 4,500 to 5,000 average. And for anyone who's written a pipeline, you'll appreciate that instead of an oscillogram with these very different free spectral ranges and this slight curvature from cross dispersion, we have 4 long slits. They're straight, they're simple to reduce, and they give you the same resolution over the entire band. And we've passed PDR in July. This is for ESO's 3.6 meter new technology telescope, and we'll be on telescope in 2020. Thank you very much. So we're still trying to figure that out. We initially expected that it would be correlated because we thought that mass would be what's driving that. So we thought a more massive envelope would have a slower rise time and a slower decline rate, but it seems to be independent. I haven't heard anyone who has anything really convincing to say about that. So we know that there are varying mass envelope densities from these. We've seen 2Bs, which rise very fast and then start to decay. But for these, it's really not clear. It could be more energy.
But it sounds like you speak like an observable. Theories must have simulated this, right? So did anyone make a prediction?
Well, predictions, there are many predictions, but I would say that I did not see any consistent, within the same theoretical framework, what we should be expecting. Specifically, and the reason I say this is that we don't have bolometric detectors. And the theorists love to simulate bolometric light curves. So in this case, there may be an issue of how thermal the ejecta is, how much radiation is emitted in our specific band. And I think that the way to go forward with this is to start with the spectroscopic coverage. Once we get spectra consistently over a large sample, we'll be able to start answering questions like, is the ejecta thermalized or not? Or is there line blanketing which affects this? So I would say that's the way forward.
I was intrigued by your result of the smaller stellar radius.
Mm-hmm.
stripping or some interaction prior, and then you might expect to see a relationship between the radius and some characteristics of the material into which the supernova is expanding.
Mm-hmm.
I know you only had this one system, is that right? So
Yeah, so we're now, so this is, that's a great question, because this is exactly the projects that I'm working on now, is actually collecting sample and data of a larger set where we should hopefully be able to perform this analysis in a self-consistent way and actually find out, is this a fluke and just a little bit small, or is this really what's happening at the population level? One thing that may be related to that is, is this circumstellar material contributing significantly or insignificantly to the emission? And with spectroscopy, we'll be able to start to answer that, because it's there's a handful of events that show these signatures of circumstellar material, but by no means do we really have a full understanding of how many there are and how it's a question of density, right? How optically thick is the circumstellar material? Is it just basically fairly optically thin, so that we just see these lines, but it's not contributing to the continuum, and our temperature interpretations are not? And we just don't know yet. We don't know when we're studying it.
These are the things that will inform the theory, I think.
Yeah.
To follow up on Adi's.
Well, that's the observer in me who wants to do that, right? I want to create the data, which you then have to match.
I think her statement is that the theory should be able to predict things from first principles. But in astronomy, we are guided by observers. Thank you very much.
Okay, thank you.
Okay, I'm Zhaohuan from UNLV. So I'll talk about the observational signatures of circumplanetary disks. Okay. So first, what are circumplanetary disks? When you have a young planet in a protoplanetary disk, the young planet will open a gap. And then when you gather material around the planet and form a circumplanetary disk. And we know the existence of circumplanetary disk because all the Jupiter's moons lie in a plane. So why should we care about these tiny disks? This sounds not dynamically important. And as we heard, Cassini has a grand finale today or tomorrow, plunging into Saturn's surface. It has spent years to study Saturn and all the moons of Saturn. So moon is a prime target for our search for life. So moon is not just moon. It's where we could see lives in future. So all these moons form in this tiny disk around planet. These are circumplanetary disks. So circumplanetary disk is important for moon formation. And also it's important for planet formation too. So in this plot, it shows that if you do not consider the accretion of the circumplanetary disks, just allow the planet start with a hot star and cool, you will follow this track, the lower track. But if you consider the energy will be added to the planet by the accretion disk, the accreting circumplanetary disks, the luminosity curve will go up, okay? And all the current exoplanets are in this regime. So the circumplanetary disk could revert the thermal history of a planet, change it from a cold star model to a hot star model. So another reason circumplanetary disks could be very important is that we may be able to observe them. For example, suppose Jupiter is accreting at 10 to the negative 5 Jupiter mass per year. It's not a very big number. This is just forming a 10 Jupiter mass planet within 1 million year protoplanetary disk lifetime. Then the accretion luminosity for this tiny disk will be 10 to the negative 3 solar luminosity. So it's 6 order of magnitude brighter than our Jupiter right now. So it means the circumplanetary disk, these tiny disks, can be as bright as M-type brown dwarf. Okay. So outshine the planet. And so far, we already have some candidates. For example, the green curve is the SED from a protostar. And the red and blue curves are the SEDs from planets, either with a hot or cold start. So these are the SEDs basically follow black body because the planet has a single temperature. But the black curve there is the SED from accretion disk around the planet. It's a circumplanetary disks. And you can see these circumplanetary disks can be brighter than the planet itself. And also, since the SED comes from accretion disk, you have hot region and cool region in one disk. So the spectrum is a mix of a lot of black body spectrum together. So the SED is a lot flatter. So we have good chance to detect these tiny accretion disks at medium free band. And this is where JWST will look at. Okay, so it has important implications for JWST. And there are two dots here. The upper two dots is from one source in one of these protostellar disks, and there are two dots and one upper limit for another source. So far we already have two candidates, which looks very red, point source in circumstellar disks, and they are consistent with this accretion disk picture. So this is where we could find these accretion circumplanetary disks at infrared. And today I'll talk about how to find them at sublimiter, and we have a great hope to find them with AMA. So normally when you give a central object mass and the object's accretion rate and some disk parameter, everything on the disk is determined. The disk structure is determined. And for the circumplanetary disks, we also know the size of the disks because circumplanetary disks normally is 1/3 of the Hill radius of the planet. So we already know a lot of parameter. And okay, thank you. So in this, we construct this simple model. Also with Sean Andrews at SMA Group and Andrew Sela at Rice. We construct some simple accretion disk model around the planet and calculated its sublimiter flux at AMA band 7, for example, with different accretion rate. So this is 10 to the -5 solar mass per year. This is 10 to the -6 solar mass per year. So this is, you form a Jupiter within 1 million year disk lifetime. And the disk is very bright. Okay, so this is AMA band 7, 5-hour 5 sigma detection. So it seems that the CPD, circumplanetary disks, can be very bright, and we should be able to detect them with AMA. And here is another model where we considered the circumplanetary disk model in our solar systems. So in our solar system, we have constraints on how Jupiter's moons forms. So we know there's a disk, and this disk, if you spread all the Jupiter moon's mass into a disk, they will follow this minimum mass subnebular model. And this is a temperature structure of the disk where you could get the ice composition correct for the Jupiter's moons. And if you put this model, calculate its sublimiter flux, it turns out even at 5 AU where Jupiter is, if this system is 140 parsec away, it's like our solar system brother has a Jupiter, we should be able to find these disks where our Io and all the moons formed with like 10-hour integration. Okay, so AMA is extremely sensitive to these tiny disks. And here is we have put a lot of models with different accretion rate and different planet mass and different alpha. And there is a correlation between the sublimiter flux and the circumplanetary disk mass. And this is 5-hour 5 sigma detection. And it turns out that AMA is extremely sensitive. So we could detect 0.03 lunar mass of dust. Okay. So even the circumplanetary disk with very, very little dust, AMA will be able to detect these. So they should be detectable. And here we shows all of these models, but in a different parameter space. Here is how close these objects are to the central star. So this is these CPDs at 5 AU, CPDs at 20 AU, CPDs at 80 AU. This is 5-hour AMA detection limit. So a lot of cases we'll be able to detect these disks unless they accrete extremely fast with large alpha value. But one problem with AMA is you have these contamination from circumstellar disks. Circumstellar disks will also emit. So if you have a circumplanetary disk embedding circumstellar disks, you'll be dominated by the circumstellar disk emission. So only if your planet opens a very deep gap, then you will decrease this circumstellar disk contamination to here, then you will be able to detect CPDs. And I'll argue there are some sources already being detected. For example, in this one is a free-floating planet with 12 Jupiter mass central objects. It accretes like 10 to the negative 8 Jupiter mass per year, and it has AMA detection with 100 microjansky somewhere here. Okay. This is one candidate. And here is another candidate. This is a circumstellar disk around the Herbig AB star. And there is a point source here, point source C. And this point source has 50 AU with 0.8 millijansky flux. So if we plot in this plot, so at 50 AU, somewhere here, 0.8 millijansky is the upper end of this parameter space. So these are another two candidates we may already have detect circumplanetary disks. So far it's promising that we have candidates for circumplanetary disks. But from a more theoretical point of view, we have a big problem. Because the dust, we know dust will drift in disks. So this is a dust drift time scale in circumstellar disks, plot in log. So you can see for 1 millimeter particles, the drift time scale is 10 to the 5th or 10 to the 6th years. So particles in circumstellar disks will go to the central star at 1 million year, roughly this lifetime. So it's still okay, we can detect millimeter emission from millimeter dust at 1 million years. But for circumplanetary disks, you see the time scale is significantly shorter because everything is smaller, the time scale is shorter. So the dust will drift to the central planet within hundreds of years. So these circumplanetary disks will quickly lose all the dust particles, millimeter dust particles, incredibly fast. So this seems to against that we will be able to detect them with AMA. So then this kind of dust drift is consistent with a lot of non-millimeter detections in these sources. These are all planetary mass objects, and we haven't detected circumplanetary disks around them. So it may be related with a fast dust drift. But we also have cases where we have detected them. So in order to detect circumplanetary disks at some millimeter, the disks needs to have dust at micron size, so they couple with the gas perfectly, so they won't drift. Or they have very high gas surface density, so that they have a small stopping time, they won't drift. Or there are substructures in circumplanetary disks which could trap particles. So the conclusion is actually inconclusive. It's no conclusion. So CPDs should be bright at sublimiter if we are optimistic, assume dust to gas mass ratio 1 to 100. But if we consider dust radial drift, we may lose all the dust particles very quickly. We may not be able to detect them. So the jury is still out. We'll wait for AMA to see if we can find these circumplanetary disks. If we do not find them, it may be consistent with dust drift. If we find them, it implies that the dust are very small or has very high surface density for these tiny disks, or there are substructures in CPDs. Okay, thank you.
This seems to be like a Russian doll. We have the galaxy as a disk inside of which we make stars. And then around each star we have a disk that makes planets. Around each planet there is potentially a disk.
Yeah.
It's moons.
Yeah, right.
Would you imagine this continuing down, also a disk around the moon, and the next other object, moon of moon?
That's a good question. I haven't thought about that. Yeah, it basically is the angular momentum conservation, right? So any disturbance will lead to a disk configuration. So whether we have moons around moon, yeah, I don't know.
This is an active time in the history of the planetary system, right?
Yeah, right.
This is happening. So I guess my question has to do with interactions with other things, because you might expect that there are rocks and objects that have already formed that might, just as today Jupiter has a lot of things inflow and toward it.
Yeah.
You might expect that perhaps a disk could get either altered or disrupted.
Yeah, right.
Which would be bad for the model. On
Yeah.
the other hand, you might also imagine that there are lots of collisions and more dust forming, and that dust could be accreted onto a disk.
Yeah, right.
So to what extent are interactions with this very active, planet-forming region, to what extent are they included in these distances?
Yes. So in these simple models, we do not consider those, but you are absolutely correct. So it related with the coupling between gas and dust particles. So if the dust is very small, they will follow the gas, form the nice disks. But if you imagine if there are already planetesimals forming the disk, they could totally decouple with the gas disk. They can do three-body interaction. They can go to CPD and fly out. Then they have very weak coupling. They could mess up things significantly. So we need to do a simulation for including both gas and dust particles with different sizes, and they have different coupling to see how much mass carried by these big bodies will end into CPD. That would be interesting project. Yeah.
Question over there in the back. Yes, observations with ALMA of circumstellar disks already kind of push the boundary in terms of ALMA's resolution. What kind of baseline or resolution would you be assuming in the Melvin modeling you did there?
Yeah, so
to resolve those circumplanetary disks?
Oh, we will never be able to resolve them, unfortunately, because the size of a CPD is 1/3 of a Hill radii. So here it shows here it shows the disk size. Here you see if the planet has 5 AU, the CPD is 0.1 AU. And ALMA has a resolution at 140 parsec, has a 5 AU resolution. So we won't be able to, even with next generation VOA, which is one motivation we put this paper, we won't be able to reserve it. If the planet is at 80 AU, it will still remain to be a point source. But the good thing with high resolution is you will get less contamination from the circumstellar disk because you have less material inside your beam. Then you will be able to have a higher contrast between the point source and the uniform background emission. Yeah.
I can use the HDMI, yeah. We'll work this out. Right, so it's a real pleasure to be here today. I'm going to talk about something that I'm not going to talk about in my colloquium, and that is to discuss elemental abundances in M-dwarf planet hosts and the implications for rocky planet dynamics. I'm going to try and convince you, first of all, that we can get interesting elemental abundances in M-dwarfs, contrary to what I thought, 20 years ago, 10 years ago. And why it's interesting in the particular case I'm going to focus on is the implications for the geophysics of rocky planets. And this is work that I am involved with, that other people are doing a lot of the important stuff on, and I will highlight them in the presentation. This is just one group. We're just one group who's working on these kinds of issues, but I thought I would take advantage of my time here to highlight some of our work. So I remember writing in NSF proposals, even 10 years ago, saying M-dwarfs are impossible. They have so many molecular features in the optical. They are very cool. We don't know a lot about them. Grr, M-dwarfs. And now I think we're in a very different regime, in part because of the apogee survey, which I'm involved in, and the fact that it's in the near infrared. And this is some very nice work by Diogo Soto and Katja Cunha et al., looking at some M-dwarf planet hosts in the Kepler field. And I know you can't see all the detail up here, but just appreciate these are like a whole bunch of individual lines that have been labeled. They did a very careful job. They did a line-by-line analysis, and they worked very hard to get, for example, the iron hydride lines correct in this star. So they added some new iron hydride lines that were not previously included in our analysis. So when you do these kinds of things, you can get beautiful abundances for about 15 elements, including the major rock building ones like silicon, oxygen, and iron. And so you can get a little up close and personal view at one of these. This is the Kepler 138 model versus the observed. And so the black is the complete line list used in this work, and the blue is the observed spectrum. And again, there's highlighting Diogo down there. And again, we're finding continuum. We're doing a pretty darn good job, in my opinion, of M-dwarf, certainly better than when you looked at the low resolution M-dwarf spectrum from Sloan that you thought we could do. Okay, so why do you care about this? Well, if we make some assumptions, and we are also working on showing that those assumptions are not crazy, but if you make the assumption that the refractory elements, things that like to condense at high temperatures, build rocky planets in the same proportion to what they appear in the star, then you can get quite different mineralogy for different planets. And this is work led by Cayman Underborn and Johanna Teskey, and then people at the Department of Earth Sciences at Ohio State, Wendy Pinheiro and Scott Hull. So this again is an artist's conception. Planets don't look like this, but to highlight in Kepler 102 versus Kepler 407 that there's a fair amount more garnet in the right-hand side one, Kepler 407, because of the higher silicon to magnesium ratio. And garnet has very different properties than olivine, which makes up an important part of the Earth's mantle. It is stiffer, it is less likely to convect. And if you're asking the question, is something Earth-like, do we consider plate tectonics to be Earth-like? Do we consider having similar mineralogy, similar water content, those kinds of things to be the same? This is an important question. And I think one of the things we'd like to highlight on this is one of the ways we can test the assumption that the refractories go into rocky planets in the same ratios that they go into a star to first order, Mercury is an exception, is that with the best measured test planets, I think we got those 50 mass radius relationships, we can, and if they're around stars that have interestingly different chemistry compositions, we can test its effect on the mass radius relation. We do predict that these things should have different mass radius relationships depending on their composition. So Cayman took a close-up look at two of these systems that I showed you in the last slide, and they are definitely different in this ternary diagram. If I can find the magic, I'm not sure I can. But let's just say your Kepler 102 is down here at relatively high magnesium compared to silicon, and Kepler 407 is among the higher in silicon to magnesium content. And here, they've been plotted on here, abundances from apogee and also abundances from Atabekian. Oh, sorry, these are just apogee. We also looked at Atabekian at all abundances. And again, when you have geophysicists, they can do things like make phase diagrams and tell you that in this system, in this rocky world, if it has the mass and radius of the Earth, this is what its mineralogy would look like. A fair amount of olivine, not so much garnet, and in this particular star, or this particular planet, we would have a lot of garnet. So that has implications. So that was something that was interesting, again, in terms of the ability of the mantle to convect. So Cayman decided to look even more detail at this, and we understand that we don't understand everything about how plate tectonics works on the Earth. We don't know what initiates it, that kind of thing. But we do know that if you try to shove a plate down and it doesn't keep going down, it's too buoyant, that chemically speaking, plate tectonics will not happen. So we're not going to answer all the questions here about whether or not plate tectonics can happen on these worlds, but we can answer the question whether or not it's chemically possible for it to happen. And what Cayman found was that sodium and potassium, the light elements, the light alkalides really screw up the ability of, if you have too much of that, it screws up the ability of the plates to go down and keep going down. So on this particular, excuse me, oh, there it is. I kept trying to use the wrong one. On this particular plot here, we've got silicon, we've got sodium. Here are the various kinds of rock. People tell me these things are rocks. Here's where the Earth lies, and we have basalt. Basalt will go down, But a lot of the worlds up here, if we make assumptions about sodium, which is tricky, are going to be so light that the crust will not want to go down. And you will not get plate tectonics because of all the frickin' sodium up here keeping your rocks too light. And that was unexpected, and that annoys me because sodium is actually a little bit hard to measure in some of these M dwarfs, and because it's not a refractory element, so how much of it gets incorporated into the rocky world. Right now we have to assume. We would love to test it, for example, with white dwarf debris disks. And then the last slide I have is basically saying to Tess, we can do an awesome job with your M dwarfs and getting important elements in there that you should care about when you're looking for Earth-like planets. And I wanted to highlight, I'm going to talk more about AS4 in my talk, but we are aggressively going after planet host candidates that will be observed by Tess. Thanks. So Cayman runs his kind of condensation models for the solar system, starting off with solar abundances. And he gets the Earth, he gets Mars, and he gets Venus in terms of the mass-radius relationship, which I think is a pretty good constraint on their interior composition. He screws up Mercury, because everybody does, because it has too large of an iron core. So again, my argument here would be that I think that assuming refractory elements, host star, and rocky world is a good first-order assumption. It is obviously a crappy second-order assumption, but it's better than assuming everything has the sun. I would like to test that, but I do think that assuming solar for everything is a bad thing. You know, especially for Kepler 444, which is around a thick disk star. And that.
Hi. So first of all, thank you. I think this is really very interesting. But the native skeptic in me thinks that it's difficult enough to understand tectonics on the Earth.
Yep.
So how seriously should I take diffusion rate restyle and based just on the composition of the element?
Oh, thank you so much for asking that question, because this is an important point, and we'll see how well I do in answering it. So my feeling is, just the first feeling I have is, we don't understand how magnetic fields work in the sun. We don't understand solar activity, and yet I think we've learned a lot about activity in stars by being willing to think about looking at activity in other stars, even though we don't fully understand the sun. And so I would argue that now the difference there is we can actually see activity in other stars, and until we get like mass-radius relationships here and more white dwarf debris disk measurements, I'm a little bit, we're not quite in the same observational range. But the other thing I would say is, I think if you have a beautiful model that ends up needing something to go faster than the speed of light in order to convect, that you can decide that that planet is not going to have plate tectonics. And that's one of the things we're approaching here. We're saying it doesn't matter what else is going on in the planet. You can shove that thing down as hard as you want. It's still going to want to float back up. And that just means that Earth-like plate tectonics will not happen there. Whether or not you can have upwelling, something else going on, that's fine. We need to think more, I think, harder about non-Earth-like ways for climate to be stabilized and things like that. But that's kind of my reaction there, is that we understand the physics, we understand buoyancy, and so the chemical criteria needs to be met. And if that's the first question, then if other criteria are met, then that's also important to know. So I guess I'm saying we're thinking more about impossible, more likely, but yeah, I agree, definitely is not yet in our to-dos.
Well, in the art of astronomy is to reduce the truth of a small number of facts.
Right.
We've been quite successful in cosmology.
Yeah. Yep.
Thank you very much.
Thanks.
You can ask now, maybe by the.
Well, I just wanted to comment. We went able to test this observation both along with radio observations, where we think that you might need plate tectonics to generate a magnetic field in a terrestrial planet. So if we detect auroral radio bursts from a nearby rocky planet, very
trick.
different line of evidence that there's different tectonics going on.
Thank you.
That's very interesting.
Hi, I'm Piero Rosati. I'm from University of Ferrara. So for those who were at the talk yesterday, oh yes, sorry. So yesterday I took the opportunity to show the tremendous progress that were made over the last, I would say, 5 years in a number of lensing applications, strong lensing applications. Here there is a list. Okay. So in recent years, actually, this progress, as we have seen this progress in many different fields, and the mass distribution of on galaxy and cluster scales, especially has been tremendous. The progress in cosmography in trying to measure H0 down to 5% level with time delays, and obviously the discovery of the most distant galaxies out to Redshift 11, microlensing, small-scale structure, and so on and so forth. So it's important to remind that everything is been driven. This progress has been driven mainly by observation. The lensing equation has been there for many years. So just remind you that we need to, if you want to map, so once you have in the strong lensing regime and a given source is split in 2 or 3 or multiple images, then you need to know your surface mass densities, because the surface mass density determines the deflection angle, and this via the geometrical effects, of course, allows you to map images on the source plane, on the sky plane, the image plane, or back and forth. Okay, yesterday also I showed that if you have enough constraints these days, you can you can reproduce these multiple images with amazing precision, down to a few tenths of an arcsecond. But these are, it's true that now these days we have a lot of constraints, but also there are a lot of parameters. So, you always wonder, I may really be able to do this because I know the answer, basically, right? And plus, with these models, you never know whether the best fit model you find is actually the unique solution, because the parameter space is quite large. So in a few years ago, you might know the story, there was an event which actually gave us the opportunity to really make an experiment on how good these models are, what is the predicting power of this, and then to do all this great astrophysics and cosmology. And so actually it was back in '64 that there was this paper by Refsdal. These are the days, remember that general relativity wasn't really the main theme. And he said, what if, if there is a supernova behind the galaxy cluster, and this gets split, in multiple images, and we measure the time delay of these multiple images, we can learn a lot about H0 and the scale, the mass of the lens, and so on. So, after 50 years, we had this great opportunity. This is a clash clusters that we study, and we knew quite well that there was this. This is just the core of the cluster. For people who know, this is the central galaxy, the BCG, and we knew that there was this beautiful spiral that in this clash thing we used to call the octopus galaxy. This spiral face-on spiral galaxy is a ratio 1.5, which was split. So it has 3 images: one in the core, which actually even double image partially, and there is another one here. Okay, but then in November 2014, Pat Kelly and collaborators find basically by follow-up, taking another image after clash as part of another program, GLASS, by comparing the 2 images, it was obviously a great event here, transit event, and it turned out to be a supernova, and then later on we understood it was a core collapse supernova very similar to 87A, at least from the light curve. But anyhow, you see, it produced this Einstein cross, okay? And because it's further magnified, further lensed by this cluster galaxy, okay? Which is lensing a supernova, which happens to live on this spiral arm of this background spiral at ratio 1.5. The cluster is a ratio 0.54, okay? So if you just remove with just a little bit of trick using the color, the many bands we have in clash, you can you can just highlight this galaxy and better appreciate the multiple image. And now that we have the model, this is actually how the galaxy would appear in reality. This is what it is. It's so small, because it's actually 1.5 after all, and this is what happens, right? Now, okay, so at that point, the model at that point, I didn't, you saw that I should have said this. The model at that point indicated, it wasn't very accurate because we didn't have a lot of redshifts and constraints to really do this modeling right. And so, but you see that it was already clear that we were looking at the supernova now, and this image was the supernova here probably would have been there several decades ago. It wasn't clear there when. People said in the 70s, in the 80s. Nobody was looking, of course, but it was quite clear that the next reappearance would have been in the future. But again, at that time, the models were not good enough. So we launched this program with my student Claudio Grillo when he was at DART in Copenhagen a couple of years ago. Again, using this fantastic multiple integral field spectrograph MUSE on the VLT, which allows you, to probe the whole redshift range between the cluster redshift and redshift 6.4 with the integral field spectrograph. So basically you can then measure the redshift of all the cluster galaxies and all the background sources, all really crucial ingredients for enabling high precision lensing model. And so, but with MUSE we can do more. Because you can make, you can do a lot, or you can just tune it. You can go through your cube and make an oxygen 2 narrowband image, and you beautifully see, because here the spiral, and there is enough, resolution and signal to noise to actually make kinematic maps at redshift 1.5. Okay, so this is basically you can do kinematics at redshift 1.5 with the same level of detail you could do in the field at redshift 0.1. Okay, but what is important here, apart from the fact that you could do velocity curves and so on, that this allowed us to identify all the multiple images due to the knots, because lots of start forming knots in these spirals, and without having this information, it's really hard to really uniquely identify the multiple knots in these other images. And these are all, again, very important inputs for the model. The model was done. And it was we were able to reproduce the multiple images with an RMS scatter of 0.26 arc-second. More importantly, it was also predicting the time delay, the short scale days time delay of the four supernovae, of the four images of the supernova, what is called S1, S4. Okay, the Einstein cross, that I showed. At that point, and this is the model. This is the data for the three images of this galaxy. This is what the model can do, okay? So at that point, we realized, Tommaso Treo, that it was a great opportunity here, that we could, for the first time, no cheating, we would have said, okay, we could run a blind test and say, okay, now you tell me, now meaning we ask 6 modelers, okay, 6 lensing experts, and now you tell me when the next image of the supernova is going to reappear. So when, where, okay? And this is a great test, again, to really try to understand the systematics of these lensing models, because they are different. There are parametric models, parametric-free models, and so on. But it was critical to get this spectroscopic information to enable all this. Otherwise, so to just recap, that was the situation then. We knew that this was going to come out again within a year, plus or minus 4 or 5 months, depending on the model. So the challenge was launched. All the modelers had to deliver the models, of course, before HST campaign. Otherwise, so easy. Otherwise, someone would say, I found a bug, but okay, I won't tell you who. But what happened was, that was, when the supernova was discovered. In fact, this was when it was peaking around here, around April 2015. So at that point, that was the prediction, at least that we did, that it would have basically become bright enough again to be observed with a one-orbit exposure with Hubble and with ACS, and we predicted it would have to reappear right here, and so when it was late 15, that was our prediction, and this is when it came out, December 2015, right there. So at that point, of course, the interesting thing was to compare the prediction of all these models to really try to understand their systematics and where we were doing right. But, it's quite interesting. And so this is just to show you, this is these contours here are basically the observation of the reappearance, meaning that at the point where it reappeared, we know when the time delay, we know also the magnification, because in order to reappear, of course, you have to get to a given brightness, so it was detected with Hubble, and this is what it was found, right? So our prediction was here. There was another model who did pretty good by Oguri, okay? But I found this, the fact that a couple of models, some that had some problems, were able to make this prediction is not a trivial thing, because I just remind you, that's my last statement, that in order to make this prediction, you need to understand the potential really very accurately, because you need to understand the first derivative of the potential, which gives you the reflection angle, where it's going to reappear. The error here was 0.3 arc second, okay, on the reappearance. You need to understand also the magnification and the time delay, because this gives you also when it's going to reappear. And the time delay depends on the, as we know, on the integral of the potential along the line of sight, along the photon's trajectory, and the magnification depends on the second derivatives of the potential. So again, the fact that you're able to make this prediction, really, it is telling you that these days, these models really have reached a high level of maturity and precision, because, again, you need the full knowledge of the potential of these clusters and all this, the small-scale structure of the mass distribution to make this prediction. So I'll stop here. Well, as you know, this would, okay, so unfortunately this was a type 2, which means, it's very flat, right? People here are more expert than me. So which means that, the follow-up paper on the real time delay determined from the peak of the reappearance has not been, the people are working on it, but we know that the peak is not going to be determined with an accuracy of better of 5 days, they tell me, Pat Henley and Steve Rodney, they tell me. And so that's going to be a problem. But as you know, H0 these days is measured with that kind of accuracy in much smaller systems, in this galaxy scale system. Here, we will see, but it's going to be a challenge because, the mass distribution is complex, but, the mass distribution, the complexity of the mass distribution was into these models. So we'll see. But yeah, the fact that there is going to be this 5 days error, it might actually limit that kind of experiment. Oh yeah, absolutely. That would be fantastic. Okay. There's going to be?
Are there going to be any more images appearing, or is that it?
Okay, so this is still partially embargo, partially not. But so by doing,
You said that galaxy was actually a double, right?
right, it's partially also lensed.
Okay.
Only half of it, okay? Because of you see this thing?
Okay.
Is it here? This bright spot, this blue spot. There is the critical curve goes right on it. So by doing the follow-up, they were trying to. At some point, this light up, went up, went down after 2 weeks, and then went back after. So the interpretation is that this is probably a micro-lensing event of a single star ratio 1.5 with a magnification of several thousand. So it could be,
Not the
so
supernova.
yeah, so not the supernova.
Okay.
But this shows that if we were monitoring this cluster with this kind of candidacy, which nobody has ever done, perhaps other of these events might come up.
Okay.
Okay.
Back upstairs. You know how to get back and everything?
Yeah, I do. Don't worry. Okay.
Anyway,
Okay.
well done.
Thanks.
Days, right?
Good. Yeah, it's been quite a ride. Thank you.
That was cool. I had one more question for you, but I don't know if you have time.
You know the story probably. You knew the story of Presto. This one.
I
You heard.
think I'd heard about it, but this was really something
Okay.
not very nice. Do you have like 2 minutes? I had one more question for you.
Absolutely.
I forgot to ask you yesterday. So you know the stuff we've been doing with the splashback radius, right? The second
Yes,
turnaround radius,
yes.
and measuring it in real galaxy clusters.